Hello, my name is Tom Soares, and today we will be discussing an article called Bifurcation of Periodic Orbits in a Chemical Reaction Problem, which was written by A.B. Poor in 1975. Before we begin, I wanted to give a quick overview of what will be discussed throughout this presentation. First, I will be discussing a bit of the background required for this article, and that includes dynamical systems, in particular, ordinary differential equations, or ODEs for short. We will also discuss how to solve what eigenvalues are and what general solutions to ODEs look like. Delving further into ODEs, we will discuss nonlinear dynamics in the form of stability analysis and bifurcation theory. Lastly, we will tie together mathematics and chemistry by the law of mass action and discuss the theoretical chemical model known as the Brusselator that is presented in this article. I will then discuss the methods used to analyze a particular behavior of the Brusselator and its findings, and give my overall assessment of this article. I will end this presentation with discussing some of the relevance of oscillating systems. Dynamical systems, roughly put, are systems that evolve in time. In particular, we'll focus on chemical reactions and the systems of differential equations that represent them. This is known as chemical kinetics. Chemical kinetics illustrates the connection between mathematics and chemistry and is the study of how fast chemical reactions proceed from reactants to products. This is to be contrasted with thermodynamics, which deals with the direction in which a process occurs, but tells nothing about the rate. Before we continue with the background on this article, I wanted to give an example of an oscillating reaction known as the Briggs-Rosher reaction. This is a chemically unstable system that undergoes numerous reactions, all occurring simultaneously, until finally the system reaches a steady state, which is its final color of dark blue. And as you can see here, the dark blue color goes away, changes a few times, and goes back to dark blue. In order to understand the rates of these oscillating reactions, or just chemical reactions in general, we must first go back to some linear algebra and recall a concept known as eigenvalues. In order to find the eigenvalues of a system of ODEs, we must first transform the system into its matrix form. On the bottom left diagram, I have an example of transforming a general 2x2 system of ODEs into its matrix form. Once we have the matrix form, eigenvalues, lambda, have the property such that AU equals lambda U, where A is an n by n matrix and U is an n-dimensional non-zero vector called the eigenvector that corresponds to the scalar eigenvalue lambda. We can find eigenvalues by finding the determinant of the matrix A subtracted by the identity matrix multiplied by the scalar lambda and setting it equal to 0. On the bottom right diagram, I have an example of how to find the eigenvalues of a 2x2 system. In addition to AU equals lambda U, eigenvalues also occur in solutions to systems of ODEs. In fact, solutions to the general system of ODEs, x prime equals ax, are of the form x equals eta times e to the power of lambda t, where lambda and eta are eigenvalues and eigenvectors of the matrix A. Notice that lambda, the eigenvalue, is associated with the exponent of this solution. Imagine what would happen if lambda was a positive value and we took large values of t. Then this solution would blow up to infinity. However, if lambda was a negative value and we took large values of t, then the solution would tend to 0. Hence, eigenvalues are critical in determining the stability of a system. Now that we know how to find eigenvalues of a system and what they mean, we move forward to stability analysis. In our ODE system, steady states, also known as fixed points, stationary points, or equilibrium points, are the set of values where the entire system is equal to 0. Particularly in closed chemical reactions, these would be called equilibrium points, as the net production of products would be 0. What we will be doing in the next few slides is analyzing the stability of these steady states, specifically in a 2x2 autonomous system. Autonomous just means that the variable in which we take the derivative with respect to, in this case t, does not appear at all in the right-hand side of our equations. In addition, we will denote our steady state as the point xs, ys. Despite having the name steady states, not all steady states are stable. For example, think of a boulder placed at the very top of a hill. A slight perturbation of this boulder would cause it to roll down the hill and not return to its original position. This would be an example of an unstable steady state. However, now think of a boulder placed at the very bottom of a valley. A slight push left or right would eventually cause this boulder to return to its original position. This would be an example of a stable steady state. There are several types of stability: nodes, saddles, which happen to always be unstable, and focus, which are also called spirals. The diagram on the bottom right illustrates the different types of stability depending on the different characteristics of the linearized matrix of our system. We will delve deeper into these characteristics, particularly the trace and the determinant of our matrix. As mentioned before, eigenvalues determine the stability of a steady state. Let lambda 1 and lambda 2 be complex eigenvalues of a 2 by 2 system. They will have the form lambdas equal a plus or minus bi, where a denotes the real part of the eigenvalue and b denotes the imaginary part. For the first case, let's let b equal to 0 so that all eigenvalues are real, and let's make both eigenvalues negative. This would produce a stable node. This is illustrated by the first diagram. As you can see, all trajectories head towards the origin, which is the stable steady state in this example. For the second case, let's let all eigenvalues be positive instead, and still both real. This would yield an unstable node. As you can see in the bottom diagram, all trajectories head away from the steady state of 0, 0. This is an example of an unstable node. For the next type of stability, or in this case instability, let's still have b equal to 0 so that both eigenvalues are real, but have the eigenvalues be of different sides, one positive and one negative. This produces an unstable saddle as illustrated in this diagram. As you can see, all trajectories are parabolic in shape. While one eigenvalue attracts it to the steady state, the other repels it, causing this saddle-like behavior. For the last type of stability we'll be looking at, we let our eigenvalues be complex, so that b is non-zero. For the first case, assume that the real part, a, is negative. This would produce a stable focus, as illustrated in the top diagram. Here, all trajectories spiral inwards towards the stable steady state of 0, 0. For the second case, assume that the real part A is instead positive. This would produce an unstable focus as illustrated in the bottom diagram. Here, all trajectories spiral away from the steady state of 0, 0. These scenarios serve as yet another illustration of the real part of the eigenvalue determining stability. Positive eigenvalues implying instability, and negative eigenvalues implying stability. Since in this article we will be looking at 2 by 2 systems, there is a very useful shortcut to determining the sign of the real parts of the eigenvalues by using the trace and determinants of our matrix. The trace of a matrix is given by the sum of all the elements on its main diagonal. The determinant of the matrix is given by the product of the main diagonal elements subtracted by the product of the off-diagonal elements. If the trace of a matrix is negative and its determinant is positive, then both real parts of the eigenvalues will be negative, thus producing a stable steady state. If either of these conditions is broken, then the steady state will be unstable. The characteristic polynomial of our matrix, which is the equation that we use to solve for our eigenvalues, is given by this expression here. This shortcut and property of 2 by 2 matrices will be very useful when analyzing the steady states of the problem discussed in this article. Now that we know how to analyze stability of steady states, let's take a look at what happens if a steady state were to change stability due to some changes in parameter values. If this were to occur, then the system has undergone what's called a bifurcation. A few examples of bifurcations include, but are not limited to, saddle node, transcritical, and pitchfork, which are illustrated by this diagram on the right. Here, as the parameter mu changes, so does the number of steady states and/or the stability of steady states. For example, solid lines represent stable steady states, whereas dashed lines represent unstable steady states. In addition, different curves may represent different steady states. More pertinent to this problem in the article is what's called an Andronov-Hopf bifurcation, or just Hopf bifurcation for short. This occurs when a steady state goes from a stable focus to an unstable focus as our parameter mu crosses the imaginary or vertical axis. A Hopf bifurcation produces what are called limit cycles, as faintly seen in this right diagram here. We will be discussing this in more detail later on. While now having the tools needed to analyze a linear and autonomous ODE system, what happens when we have a nonlinear system? Well, in this case, we would have to use linear stability analysis. One form of linear stability analysis is using a special matrix called the Jacobian matrix. We can use the Jacobian matrix, J, and evaluate the matrix at our steady state. The elements of the Jacobian matrix are given by the partials of each function with respect to each of its variables across the rows, as illustrated in this diagram. The Hartman-Gromman theorem states that if J is hyperbolic, then the qualitative behavior of this matrix, which is also known as the linearization of the system, is the same as our original systems. A matrix is hyperbolic if and only if all of its eigenvalues have real parts non-zero. This is a very useful result, as now we can examine the eigenvalues of this matrix the same way we would in a linear system, assuming, of course, that all the real parts of our eigenvalues are all non-zero. After a detailed look into systems of ODEs, the question is, now why do we care about them? Well, we can apply what's known as the law of mass action to transform chemical reactions into a system of differential equations. The law of mass action states that the rate of an elementary reaction is proportional to the product of the concentration of the reactants. We must also keep in mind the stoichiometry of the reaction to have the correct constants. Here's an example of a simple reaction transformed into a system of ODEs. The rate is given by K1A squared B, and so we can model the concentrations of each species in this reaction by the following system. In this example, both dA dt and dB dt are negative due to the reactants not appearing on the right-hand side of our reaction. dC dt is positive because C does indeed appear on the right-hand side. Focusing more on the stoichiometry, there is a coefficient of 2 in dA dt due to the total change in the concentration of A being 2. Similarly, there are coefficients of 1 in both dB dt and dC dt due to the total change in the concentration of each species being just 1. Finally, the oscillating reaction that we are concerned with, and that is analyzed in the article, is an autocatalytic chemical model known as the Brusselator. The Brusselator model is a famous model of chemical reactions with oscillations. Its scheme is given here in the diagram on the top right. As you can see, there are 6 different species and 4 different reactions. The Brusselator was proposed by Ilya Prigogine and René Lefebvre in 1968, and the name is a portmanteau of Brussels and oscillator, hence the name Brusselator. In this model, the species A and B are assumed to be in vast excess and thus can be modeled at constant concentration. In addition, the species D and E are assumed not to participate in any further reactions, making their concentrations irrelevant. This means that the only species we are interested in are X and Y, which are both autocatalytic as well. Following these conditions, and applying the law of mass action, we get the following system of ODEs below. The current system of ODEs that we have for the Brusselator contains 6 parameters: K1, K2, K3, K4, and A and B. Through what is known as non-dimensionalization, we can rescale our system's variables and parameters to not only make them unitless, but to also have fewer parameters. This simplifies the system by a great deal. If we scale the variables by the scheme shown here on the left, and through a bit of algebra, we get the new simplified and more commonly used Brusselator ODE system shown here on the right. Notice that we now only have 2 parameters, A and B, instead of the previous 6. Due to this simplification, we can now find the steady state of the system quite easily. Remember, this means when our system is equal to 0. Thus, the only steady state is given by the point A, B over A, where A is non-zero. Despite our new simplified system being much simpler than the original unedited system, we are faced with the problem that the system is still nonlinear. Thankfully, we can use the Hartmann-Grobman theorem to analyze the stability, or stabilities as we will soon see, of the steady state. By taking the partials of the simplified Brusselator, we get the Jacobian shown here at the top left. Thus, evaluating at our steady state yields the following matrix in the middle. By applying the characteristic polynomial from our 2x2 lemma, we get the characteristic polynomial shown here. By setting this polynomial equal to 0 and solving for lambda, we get the following eigenvalues shown on the right. We will now discuss the various cases as our parameters a and b vary. In order to analyze the steady state, we will fix the parameter b and analyze the steady state as the other parameter a varies. We will first look at the case where the discriminant portion of the eigenvalue, which is the expression inside the square root, is positive. This implies that b is greater than the quantity a plus 1 squared. If b minus 1 minus a squared is greater than 0, then both eigenvalues are real and positive. If you recall, this produces an unstable node. On the diagram on the right, I plotted a few trajectories with different initial conditions and the steady state marked by the black rectangle, when a equals 1 and b equals 5. As you can see, all trajectories diverge away from the steady state. For the next case, we assume all the same conditions from the previous slide, except consider the scenario when b minus 1 minus a squared is less than 0. In this case, both eigenvalues are still real, but now they're both negative. This produces a stable node. The diagram on the right shows several trajectories with different initial conditions and the steady state marked by the black circle when a equals 3 and b equals 2. As you can see, all trajectories converge towards the steady state. We will now consider the case when the discriminant is negative. Thus, b is less than the quantity a plus 1 squared. This means that we now have complex eigenvalues. If we take the case where b minus 1 minus a squared is less than 0, then the real parts of our complex eigenvalues are both negative. This gives a stable focus. The diagram on the right shows multiple trajectories that all spiral inwards towards the steady state when a equals 1 and b equals 1.9. Perhaps the most interesting case that leads us into the problem discussed in the article is the orbital behavior exhibited in each of these diagrams. Here, we have the same conditions as in the previous slide, except we make the real part of the eigenvalues positive. This produces an unstable focus. These diagrams illustrate the same steady state when a equals 1 and b equals 2.1, but with two different initial conditions. The diagram on the left shows the behavior of a trajectory when we start far enough from the steady state. We spiral in towards an orbit around the steady state, but of course never reach the steady state itself. On the diagram on the right, the trajectory starts close enough to the steady state so that it spirals away from the steady state and towards an orbit around it. This behavior is known as an attractor and is called a limit cycle. This is where we start discussing the periodic orbits of the Brusselator. Finally, we have the last case of parameter choices. If we make the discriminant negative, but instead make the real part of the eigenvalue 0, we're now in the case where we have pure imaginary eigenvalues. This means that the matrix is now non-hyperbolic, which means we cannot apply the Hartmann-Grobman theorem as we have been doing for these past few examples. The diagram on the right illustrates a trajectory far enough from the steady state at the non-hyperbolic condition of the steady state, particularly when a equals 1 and b equals 2. As you can see, the trajectory keeps spiraling inward but doesn't approach the steady state, and instead creates this very dense orbital region here. This non-hyperbolic condition is the Hopf bifurcation point. Since we cannot apply the Hartmann-Grobman theorem, we must find a new way to analyze the system at this particular bifurcation point. This is where we will now discuss the article's objective, as well as its methods used. The investigation of the Hopf bifurcation finally leads us to the objective of this paper, which was clearly stated near the beginning of this article. The objective of this paper is to show the existence of periodic orbits in a theoretical autocatalytic model, the Brusselator, and show that the orbits are asymptotically orbitally stable. We must also find ways to analyze the non-hyperbolic condition where we have pure imaginary eigenvalues, as the standard Hartmann-Grobman theorem does not apply in the non-hyperbolic case. The article discusses several theorems that summarize the Hopf-Friedrichs bifurcation theory. In particular, we will focus on the three algebraic conditions required that prove the existence of a Hopf bifurcation, and thus the existence of limit cycles. Condition 1 requires pure imaginary eigenvalues. This is known as the non-hyperbolicity condition. This is inherent to our problem since our matrix at the bifurcation point was non-hyperbolic to begin with. Condition 2 requires our eigenvalues pass the imaginary axis at a non-zero speed. This means that the rate of change of the real part of our eigenvalues is non-zero. This condition is known as the transversality condition. Lastly, condition 3 requires a trapping region. This ensures that our trajectories do not spiral out to infinity and do indeed converge to a limit cycle around our steady state. This last condition is known as the genericity condition. The article uses different variables and parameters in order to follow the theorems closely. For example, they use A equals gamma 1, B equals gamma 2, X equals x1, and Y equals x2. However, I will stick with the same parameters and variables as from before for continuity purposes. I also adjusted some of the figures to have matching parameters and variables, as well as edited some of the variables and parameters in theorems to not cause confusion with our previous work. We will follow the same scheme as before. We fix B and vary A. In order to examine the non-hyperbolic case, the article perturbs the varying parameter A by a non-zero epsilon. By substituting the non-hyperbolic condition, as well as the perturbation of A, into the Jacobian matrix of the steady state, we obtain the matrix here below. By using the same methods from earlier in the presentation, we obtain the following real part of the eigenvalue denoted by this equation in the red box. By substituting 0 in for epsilon, we obtain the eigenvalues of plus or minus I times the absolute value of A. We will need this eigenvalue later in order to find the left and right eigenvectors associated with it. For now though, if we take the simple derivative of the real part of the eigenvalue with respect to epsilon and evaluate it when epsilon equals 0, we obtain negative A. Remember, A was non-zero by assumption since A appears in the denominator of the steady state. This fulfills condition 2 for the existence of a Hopf bifurcation. And remember, condition 1 was already fulfilled since this was non-hyperbolic to begin with. The last condition, on the other hand, is a bit tricky. From theorems 2.3 and 2.4 in this article, along with multiple partial derivatives and some non-zero constant vectors C that were derived from some specific integrals listed in the article, and our eigenvalues and corresponding eigenvectors, we can finally evaluate this beast of a condition. At the very end, this returns a positive term, which is non-zero. With a non-zero term, we ensure that our region is trapped and our trajectories will not spiral out to infinity, and will instead be attracted to our limit cycle. Thus, this fulfills condition 3. Moreover, as a result of this non-zero term, theorem 2.3 stated that if delta 1 prime of 0 is non-zero, then the orbit is stable. Since the left-hand term of this expression is non-zero, this implies that delta 1 prime of 0 cannot be 0. Otherwise, this entire expression would be 0. Hence, this result yielded us both the satisfaction condition of condition 3 and the stability of the periodic orbits. The article also goes on in a similar fashion by instead fixing A and varying B. This is, however, redundant since this is a 2x2 system with only one steady state. Fixing both variables and analyzing them separately would only yield results with the axes switched, but still giving the same results. To illustrate the findings proven by the methods in this article, this is a figure that shows just the limit cycles of the Brusselator, when A is equal to 1 and B gets closer and closer to 2 from above. The findings in this article were not surprising as it came directly from its objectives. Poor proved the existence of periodic orbits by fulfilling the three conditions required for a Hopf bifurcation. As a consequence of the proof of these periodic orbits, fulfilling condition 3 of the existence of a Hopf bifurcation also satisfied another theorem that gave the stability of these periodic orbits. These findings are important because it gives algebraic methods to investigating a system whose linearization is non-hyperbolic, meaning that the standard Hartmann-Grobman theorem approach to analyzing a nonlinear system was inapplicable. There were a few things that worked really well in this article. Firstly, since it met its objectives by a series of mathematical proofs, this means that there is certainty in its results, leaving no room for ambiguity. Secondly, it clearly stated and summarized the theorems needed and used in order to meet the objective of stable periodic oscillations in the Brusselator. Poor also showed most of the steps taken to fulfill the methods required. He left a bit of the algebraic workout, but he at least showed each result of the most important factors, the perturbated and substituted Jacobian matrix, as well as its eigenvalues and eigenvectors. There were, however, a few things that I think Poor could have done to improve his article. Firstly, from what I found, Poor and his references did not give the scaling scheme in order to get the Brusselator ODE into its simplified form. That was definitely some required background needed to understand how he went from the original chemical reaction to the simplified system of ODEs that we worked with throughout this presentation. Secondly, he did not need to fix both variables during the methods portion of this article, as doing so would still yield the same results, but with switched axes. It was an unneeded portion of his article, and thus both redundant and an overcomplication. Thirdly, he claimed in the beginning that the existence and stability of periodic orbits can be shown through algebraic means when certain simple algebraic criteria are met. Even with a math degree under my belt, the theorems are pretty difficult to read. They are, at least, much easier to apply, but certainly not simple. Lastly, Poor does not discuss the significance of oscillating systems, and is only entirely concerned and focused with the existence of periodic orbits. This leads to my next slide, where we will finally discuss some of the significance of oscillating systems. Oscillations occur in many instances. One example is circadian rhythm, and in particular, a human sleep-wake cycle. Roughly put, our body's clock works in such a way that light exposure causes it to send signals that generate alertness, helping to keep us awake and active. As night falls, the clock initiates the production of melatonin, which promotes sleep and sends signals to help keep us asleep. Our circadian rhythm aligns our sleep and wakefulness with day and night, and this process repeats roughly every 24 hours. Another example of oscillations is vibration. Sound waves cause our eardrums to vibrate, and then this information is passed on to the brain. Plucking a guitar string also causes a vibration to the string, which produces sounds that we know as music. Springs are perhaps the most thought of example. Cars have shock absorbers that help ensure safety for passengers. When we go over a bumpy road, these shock absorbers help make for a smooth ride by compressing and are then pushed back to its original position. Lastly, and more science-based, is morphogenesis. Morphogenesis is the biological process that causes a cell, tissue, or organism to develop its shape. An example of this is a concept known as Turing patterns, which is the occurrence of periodic spatial patterns in nature, like stripes on a zebra or spots on a leopard. In a chemical system, if a stable steady state becomes unstable due to the presence of diffusion, then a Turing bifurcation occurs. This is another type of bifurcation that we did not discuss in our presentation. A Turing bifurcation generates these periodic spatial patterns in nature, and I think that's really cool. And that concludes my presentation. I hope you all enjoyed this video and learned something new. Thank you for watching.